Hi all, I'm Meghamala, working as an assistant professor in Institute of Aeronautical Engineering. And coming to today's topic, today I'm going to discuss about the time delays with switch primitives. So, coming to the topic, time delays with switch primitives. What are the time delays? The time delays are meant with respect to the time constraints. Okay, so for each and every module that you are designing, and being a designer, he has to concentrate on the delays as well. So with what sort of delays the input is carrying out the signal with respect to the output, and as well the delays we can the delays can be appear at the input and as well as the output. The delays can also be calculated, and in the delays, coming to the delays, we have different types of delays: time delays and as well as the event delays. So regarding this time delays and event delays, in the last modules we have discussed earlier. And coming to the right now time delays, regarding to this time delays, there are different types of time delays present in the Verilog. Okay, in the Verilog library, we have different primitives pertaining to the gates and as well the switches. So pertaining to the gates and switches, we have different types of Verilog primitives which are present in the Verilog. And coming to the time delays. So as we are discussing about the time delays, there are three types of delays which are present in the Verilog. They are rise, fall and turn off delays. So regarding what is the delay declaration, the delay declaration can contain up to three values. Okay, so they are the rise delay represent with TR, fall delay TF and turn off delay TO. So these are the declaration, the delays declaration pertaining with respect to the time. And when it with respect to the delays, usually we will represent the delay, rise delay, fall delay and as well as the turn off delay like this. Delay, this is for rise delay, this is for false delay, fall delay and this is for turn off delay. So here the time taken for the output gate changes from the time taken for the output gate, which changes its value from 0 to 1 when it changes its value from 0 to 1. So this is nothing but the rise time. So the delay pertaining to this rise is nothing but the rise delay. And when the value, if the output the time taken for the output to change its value from the 1 to 0, from 1 to 0, we are calling this pertaining this particular time as fall time. So the delay which is associated with this particular delay, particular time is nothing but the false delay. Delay false. Okay. So here the time taken for the output, when it changes its values from 0 to 1, then that kind of time is nothing but the rise time, and the delay which is associated with this delay underscore R. And when the output, when it changes its output from the value from the 1 to 0, so it's nothing but the false delay. And so there the time taken for it is to just the value when it changes its from value from 1 to 0 is nothing but the false delay, and we associated the false delay in with respect to the time constraint is TF, and in delays we usually will represent delay underscore F. And the last one is the time taken for the output gate to change its value from some high value, from some value to high impedance is nothing but the turn off delay. Usually in this turn off delay, what happens is at some particular time, the values till that particular time only, the turn off time, the switch will be on condition, and later on beyond the time limit, the switch goes to off condition. So usually for the rise time, this is the rise time we represent is from 0 to rise time, from 0 to high level, isn't it? From 0 to high level, this is a rise time, and fall time is from 1 to 0, this is a fall time. And then the turn off time is nothing but when the value, when the output values goes high. Okay, when the output value goes with the high impedance is nothing but the turn off time. Usually we are representing the turn off time as TO. So in terms of delay, we are representing delay underscore O. So this is all about the different time constraints that we have present, that they are present in the Verilog. So if only one delay value is specified, then it is used for all signal changes. So in the delay representation, we have sometimes one delay, we have 2 delays and we have 3 delays. When you have 1 delay, it means that that delay will be specified for all the signals, for all the signal changes. Okay, for all the signal changes. So usually the default value that it will change is 0. Usually for the one delay, if the element is presenting it with 1 delay of time, then it says that the fall delay is with respect to 0. So the value, the delay can also changes for all the signal changes. And then if you have, for example, 2 delays. So for these 2 delays, when it is specified, then always remember that the first delay represents with the rise time and the second delay will represent with the false time. Okay, so the first delay with respect to the rise time and the second delay represented is with respect to the false time. So TR and TF. This is with respect to the 2 delay transition. And then if you have 3 delay transition, so usually in the 3 delay transition, we have rise time, fall time and turn off time. So here, when you are in the program, if you have a 3 delay of transition signal, okay, then these 3 delay of transition signal are with respect to rise time, fall time and the turn off time. So here, if the signal is in high impedance or unknown, then the signal value will be used. Then the smaller value will be used. That means what? Here, when the signal changes with respect to the high impedance value, that means what? With respect to the Z. When the signal changes its values with the high impedance value, that is Z. So usually regarding this pertaining this statement, this statement is talking about the turn off time. So turn off time is nothing but the delay which is beyond the present one, beyond the limit. See, after this, only with this particular limit, we can write the switch will be on, and after that the switch goes to off state. Okay, that means what? Here the values are going to a high level value, that is high impedance value, that is Z or X. So X is nothing but the unknown values and Z are nothing but the high impedance values. So here, if the signal changes to high impedance values or the unknown values, then the smaller values will be used. So here at this particular, for example, at this particular point, beyond this, the switches goes to off condition, and within this limit, the switch will be in the on state. So here at this particular point, what happens is, being a designer, if the switch is in the off state, so here he can take a smaller value which is more nearest to the high impedance value. Okay, so this is all about the specifying of the delays with respect to the 1 delay, with respect to the 2 delays and with respect to the 3 delays as well. So here the representations of rise time, fall time and the turn off time. So here if you observe the rise time is going with respect to from 0 to high. So when the signal is taking its transition from the low level to the high level, obviously the 0 is nothing but the low level and 1 is nothing but the high level. So when the signal's transition is taking place from the low to high, then that particular time is nothing but the rise time. And when the signal is going from the high to low, okay, from 1 to 0, then that particular time is nothing but the fall time. So here we represent in terms of delay as delay F fall and delay underscore R rise time and delay underscore O, that is turn off time. So here if you observe this turn off time, only at this particular that switch will be on, and beyond that it will be off, and here it will be, the switch will be in the on state. So usually the designers will consider only the smaller values of that particular area. Only this particular area smaller values can be considered by the designers in order for the transition of the switches from the low to high and from the high to low. And then if the 3 values are given, for example, if the 3 values are given, then the first signal or is in the first value that it is specified is the rise time. That means, for example, in the exam point of view, sometimes the delays, it goes like 0.25 and 2.53 and 1.89. So here when such numbers are specified in this fashion, then always remember that these are the delays. Okay, so these are the delays. Usually we represent the delays with the ASH code, ASH D, right? ASH D. So this is nothing but the delay. So here in this, I'm having the three numbers. So first number I can consider is for rise time, and the second number I can consider it for the false time, and the third one I can consider it for the turn of time. So here, when the three values are given, then the first value specifies the rise time, the second will specify the fall time, and the third will specify the turn of times. And then if the signal changes to unknown value, then the smallest of these three values can be used. So here, if the signal changes with respect to the unknown values, or else with respect to the high impedance values, so in such cases what happens is the smallest of the three values. So the smallest of the three values can be considered. Okay, this is the smallest of the three numbers is 0.25, right? So the 0.25 can be considered. And then the delays are applied to any kind of signal as they can rise, fall and turn off. So here the delays can be applied to any kind of signal. You can apply the delays for the input signal and as well as for the output signal. So here the input, whatever the delays that you are giving, so such delays can be in terms of rise time, fall time and the turn off time as well. So there are no restricted only to only output of gates. And so these delays, they are not only restricted to the input as well, but also they are not restricted to the output as well. And the representations of the delay. So here, when it comes to the representation, as we discussed in the previous slides, we have there is a three ways of representing the delays can be observed. So one is the one delay format, the second one is a two delay format, and the third one is a three delay format. So here we will discuss what are these, how the delays are represented, and how we can represent the delays when it comes to when we have two delays or three delays and only one delay. So here the two delay format can be applied to the most primitives. So usually when you compare, we have three delays, right? One delay, two delay and three delay specification. But among these three delay specification, usually we'll go with the two delay specification. So here the two delay format specifications can be applied to more primitives. Okay, in most of the primitives, the two delay specifications can be applied, and who do not the outputs do not transitions to the high impedance. Why? Because here in the two delay transitions, usually we don't see any high impedance state or else the unknown state. Okay, so within the limit, the delays will be observed, and that delays will be carried out with respect to the rise time and as well as with respect to the false time. So the three delay format cannot be applied to AND gate because the output will be not Z or X for any input combination. So here the three delay specifications usually we will not apply to the AND gate. Why? Because AND gates are the very simple structures where the delays of such high delay, three delays cannot be considered to the, or else cannot be applied to such small structures. So usually, why? Because the one thing is, based on the structures, the three delay elements cannot be applied to the gate structures, and as well based on the values. See, when you are considering the AND gate, in the AND gate outputs, you will be observing the output with respect to 0, 0, 0, 1, and here anywhere you don't have, we don't get any kind sort of output as in terms of X and Z. Okay, why? Because these are the very small structured elements, very small structured circuits. So this is one of the reasons that AND gates are very small structured circuit. And the second reason is, as these are very small structured circuits, the output will not be observed in terms of Z and X. Okay, the output will only be observed in terms of the binary bits, that is 0 or 1. But the value will not exceed to high impedance values, or else they don't have any don't care condition statements. That's the reason the three format delays applications cannot be applied to the AND gates. But some other complex gates can be applied. And then the single delay specification. How the single delay specifications for all the three transition delays. See here, if you observe, we are presenting the delay with respect to the ASH, right? So ASH delay 0, 1 is nothing but the name of a particular gate, and here it is a terminal list. So as it is a terminal list, So in the terminal list, the representations of the output terminals and as well as the input terminals goes with respect to the terminal list, right? So in the terminal list, output ports will be entered first, represented first, and then goes with the input ports. So here, this is the specification of single delay. So when you observe here, we have only one delay specifications. And the second one is two delay specifications. So for this two delay specifications, as I said you, in these two delay specifications, we'll be observe the two delays. One is with respect to rise time and another one is with respect to the false time. So the rise time, as it is a two delay, one is with respect to the rise and the second one is with respect to the false. And similarly, the third one is a gate. And in the terminal list, we are representing the output terminals and as well as the input terminals. And coming to the third delay specifications, three delay specifications. So here in the three delay specifications, the three types of timing constraints will be specified. So here it is rise, fall and turn off. So rise, fall and turn off, as usual, the name of the gate and in the terminal list. So this is nothing but the specifications of one delay, two delay and three delay specifications formats of different delays with respect to rise time, fall time and the turn off time. So here we will see the specification one delay format. So this is a one delay format. So in this one delay format, this is a small syntax which shows of how to write a one delay format. So we have a module. Module is a keyword, okay, and followed with the name of a circuit that you are considering, and then followed with the terminal list. In the terminal list, so this is a port list actually. Why? Because we are starting with the module, right? So we have a module with the port list and then we have the terminal list as well. So in the port list, we will be representing the output ports, input ports and as well as the control ports, control lines. And when it comes to the terminal list, in the terminal list, we only initialize or else we only we dump the values or else we dump the ports pertaining to the input, output, okay, input and as well as the output terminals. So here module, name of a circuit, in the bracket, in the port list, we are representing the output port, input port and as well as the control ports if you have any. And then specifications of the AND gate. So here this is a one delay format, right? So the specification AND gate has 2 time unit delay. So here we are specifying this AND gate has 2 nanoseconds of delay, isn't it? So this AND gate is having the 2 nanoseconds of delay. So here AND gate with the delay of 2, isn't it? AND gate with the delay of 2 and the gate, name of a gate and then with the port list, output ports and then goes with the input ports. And then this is about the AND gate. For suppose if you are considering any buff if 4 gates, okay, this is the bidirectional gates, right? So buff if 0, buff if 1, buff if not. So these are the bidirectional gates. So in the example, if you are considering any bidirectional gate, that is buff if 0. So for this buff if 0 gate, it has 3 time units of delay. That means what? Only the delay is pertaining to the 3 time units. That is 3 nanoseconds, for example. So for this 3 nanoseconds, the representation is same. See here, we are using the buff if 0, right? As it is a bidirectional switch, always whatever the switch that you are considering, we have to write the keyword based on the switch that you are considering. That means what? If you are considering any PMOS, then our keyword must be PMOS and then delay 1 with the name of a circuit and the port list. This is how we have to write. If you are considering any NMOS transistor, for this NMOS delay of 3 nanoseconds somehow and then the name of a gate and then the terminal list. So this is how the representation takes place when you observe the keywords that you are mentioning. We have to be very careful when you are writing the keyword. If suppose you are taking any PMOS transistor, then your keyword must be small PMOS. And if you are considering any NMOS transistor, then your small word must be small NMOS. If you are considering any CMOS switch, isn't it? So for this CMOS switch, it's the same delay of 10 nanoseconds and the CMOS CM with the port list, terminal list. So this is how the representations of the keywords takes place. So when it comes to the one delay of format, here we are using buff if 0. Okay, so for this buff if 0, we have 3 time units of delay. So our keyword goes with the buff if 0 because my switch is buff if not, right? So buff if 0 with a delay of 3 and then the port list or the terminal list. And finally, I'm ending up with the end module. Okay, this is about one delay format. And now we will see the 2 delay format. In the 2 delay format, the module is a keyword and the name of the circuit that you are considering is description of that particular circuit. And then in the port list, we are representing the input ports and output port as well as the control ports. And then finally considering the gates that you are considering pertaining to the delays of that particular circuit. So here I'm considering the AND gate. So for this AND gates, I'm using like as it is a 2 delay format. I have to represent the delays in terms of 2 numbers, right? So it is a 2 delay format. One is with respect to rise time and one is with respect to fall time. So here I have to represent the 2 delays. One is with respect to 2 and 3. So here AND gate, ASH, 2 and 3, name of a gate and then the port list. Okay, and then the secondary thing that I'm considering the example as buff if 0. So for this buff if 0 as well, how can we represent the 2 delay format is the same buff if 0 because my switch is buff if 0 bidirectional switch. So buff if 0, ASH, 4 and 5. Why? Because one is with respect to the rise time and then another one is with respect to the false time. Then the name of a circuit, then the port list or else the terminal list. Finally, ending up with this, the end module. So this is the representation of 1 delay format and as well as the 2 delay format. In the 1 delay format, we are representing only the delay number with respect to the numbers is only with 1. Whereas when it comes to the 2 delay, this is for 1 delay, right? So when it comes for the 2 delay, we have to represent the delays in terms of 2 numbers, 2 or 3, 4 or 5. Whatever, with how much of delay the signal is moving forward or the signal is passing out, with that much of delay representations has to takes place. This is the 2 delay format and this is the 1 delay format. And coming to the 3 delay format. So the 3 delay format is also simple as like 1 delay and 2 delay. Here also in 3 delay format, we have a module, the name of a module and the name of a circuit that you are considering, and this is a port list. In the port list, like usually input port as well as the output port. And coming to the AND gate and buff if 0. So here, as I said, it is a 3 delay format, right? So here it is a 3 delay format. In the AND gate, this is what only we have 2 numbers. So this is nothing but the 2 delay format. Whereas here we have 3 numbers, right? So this is 3 delay format. So for 2 delay format, usually we will represent, here we have hash 2 and 3. This is with respect to the AND gate. So the delay is represented as with 2 and 3. Why? Because 2 is with respect to the rise time and 3 is with respect to the false time. And here one more gate we have is buff if 0. So here in this buff if 0, we have a delays as 5, 6 and 7. So what is this 5, 6 and 7? It is a 3 delay format, right? So I'll be having my 5 as rise time, 6 as false time, 6 as false time and 7 as turn off time. Why? Because here it is a 3 delay format. So rise time, fall time and turn off time. So this is how we will be representing 5, 6 and 7. So this is nothing but the 3 delay format. So module, AND gate, buff if 0 and end module. Finally, we are ending up with the end module. So this is nothing but the representations of delay formats with respect to 1 delay, 2 delay and as well as the 3 delay formats. And now we will see the switch primitives. So the time delays with respect to the switch primitives. So here in the switch primitives, we know NMOS switch, PMOS switch and CMOS switch. So here these are the nothing but the basic switches, and how with respect to the switch primitives the delays can be written, we are going to see now. So the instantiation of the NMOS switch. So here I am considering the NMOS transistor. So my transistor is NMOS. Obviously, I have to start my problem, or else I have to start my program with the keyword NMOS, isn't it? So here, the instantiation with respect to NMOS. So my NMOS it has no delay. So here it is, if you observe, this is a keyword and then followed with the terminal list. This is a terminal list. So if you observe this statement, nowhere we are seeing any kind of delays, isn't it? So this is nothing but it has no delay associated with it. So purely the switch has only the keyword and then followed with the port list or the terminal list. It has no delays which are associated with it. And then coming to the NMOS with delays. So here if you observe, you have only one delay. Okay, the one delay and the name of a gate and then the terminal list. So here it has a delay 1, as a delay for the output is rise, fall or turn off. So here we can see the instantiation of a delay is represented only 1, isn't it? Delay, this is delay 1. So this delay 1, it could be of rise time, fall time and turn off time. Okay, and then NMOS. NMOS delay R, delay F and 3, this is it, output list. So here terminal list. So here if you observe, we are specifying particularly delay R and delay F. That means what? This is a two terminal delay representation. So one delay, as we said, two terminal delay means 2 delays we have. One is rise time and the second one is false time. So here the delay R, delay underscore R is nothing but the rise time for the output, and then delay underscore F is nothing but the false time for the output, and the turn off time is 0. Here we don't have any turn off time, isn't it? So as we don't have any turn off time, then particularly that time is meant to be 0. So here we have only 2 times that are with respect to the rise time and false time, delay R and delay F. And MOS. So here in the previous slide we have discussed with no delays and with 1 delays and 2 delays, and now we will see about the 3 delays representation. So here in the instantiation, as I'm considering the NMOS transistor, my keyword should goes with the NMOS, and then here the representations of the delay. So as here I'm considering the 3 delay, the transitions of with 3 delay, the signal. So one is with respect to rise time, false time and the turn off time, and obviously the name of a gate, then the port list. So here it has the delay R, that means what? The rise time for the output. It has rise time, delay R is a rise time for the output, and delay F is nothing but the false time for the output. So when here in the false time, isn't it? So delay O is nothing but the turn off time. So here totally 3 different types of delays we can easily can accommodate or else associated with that particular signal. So here in this NMOS transistor switch, we have come across with 3 delays. Okay, rise time, false time and as well as with the turn off time. So when the control signal starts, when the control signals goes from low to high, then obviously that particular time distance or else the time delay is nothing but the rise time. When the signal is taking its transition from 1 to 0, then that particular time period is represented as turn off time. Okay, this is turn off time. And also remember the bidirectional switches. The bidirectional switches do not delay transmission. They rise time, fall time and are 0. So here when it comes to the bidirectional switches, so what are the bidirectional switches? Bidirectional switches are nothing but the buff if0, buff if1, tran if0, and these are nothing but the bidirectional switches. So here in this bidirectional switches, we say that the switches do not transition delay. So they do not transmit any kinds of delay with respect to the rise time, fall time and as well as the turn off time. And also remember that the bidirectional switches, they can only turn on, turn off delay associated with them. So here the delay transitions would be seen very less when it compares to the other switches. When it comes to the bidirectional with respect to the other switches, the bidirectional switches, it can have only turn off time and turn on time. But other switches, if you consider, those switches can transmit the signal with respect to the rise time, turn on time, turn off time, and as well the rise and fall time. We don't see any rise and fall time with respect to the bidirectional switches. Okay, in the bidirectional switches, we see only turn on time and turn off time. That what is turn on and turn off is, see, this is the transition taking place from 0 to high. From 0 to high value, this is a TF, isn't it? And here, this is a TF, this is rise time. Okay, and then from here to here, the switch will be on, turn on time, isn't it? Then from here to here, it is turn off time. So the bidirectional switches, in the bidirectional switches, we see only turn on and turn off delays which are associated with it. But nowhere will see the rise time, false time, or the turn off time. And then the TRAN has no delay associated with it. Why? Because TRAN is also a bidirectional switch. So here we don't see any sort of delay which are associated with this TRAN circuit. And then we will see now the representations of this TRAN if 1 and as well as the TRAN if 1 and 0 with respect to the delays, with 1 delay and with the 2 delays. So here we see the TRAN if 1 with the 2 delays. We have 2 delays. One is with respect to the rise and the other one is with respect to the fall. So here TRAN if is a switch, bidirectional switch. So my keyword should go with the TRAN if 1 and then the delay. So here I am representing the 2 delays. One is rise and fall, and then the circuit that I am considering then follows with the terminal list. So here, when the control signal changes from 0 to 1, okay, when the control signal changes from 0 to 1, obviously the output changes the delays with respect to the rise time, isn't it? From 0 to 1, obviously the switches turns on, and then when the control signal goes from 1 to 0, what happens is when the switches, when the control signals, it takes its transitions from 1 to 0, then the switch will turn off with a delay of delay F, that is false. So here it is rise time and obviously here it is a false time. So transition takes place from 0 to 1 and here it is from 1 to 0. And then here we see the rise and fall time, right? And now we will see with delay 0. So what does this delay 0 means? So it represents the initiation of that particular switch with respect to the delay 0. Why? Because here the switch for turn on, when the control signal, when it changes from 0 to 1, and then when with the same delay it will be turn off when it changes to 1 to 0. So in the one transition, we will see the switching of a transistor goes with the 2 states, on and off. It will be on when it takes the transitions goes from 0 to 1, that is from low to high. We see the switch will be in the on condition, on state, and in the second transition, then it takes its transition from 1 to 0. When it is falling down from 1 to 0, then the switch goes with the off state. Okay, so here we see the 2 transitions. One is with respect to on state and the second one is with respect to the off state. So here we have seen like in the switch primitives pertaining to the time delays, we are saying that though it is resistive switches or the normal switches, in all the switches based on the delays that you are considering. Okay, so sometimes you may consider no delay, sometimes you may have 1 delay, and sometimes you may have 3 delays. So how much delays that the signal is taking place, its transition, then remember that signal, that delays will represent with the rise time, fall delay, rise delay, fall delay, and as well as turn off delays. Okay, see here. This is with respect to the TRAN if 1. So here in the TRAN if 1, we see same rise delay and false delay. Okay, however, in the previous slide also we have discussed TRAN if 0. Though both the switches are bidirectional. So here the representations of delay goes like this: TRAN if delay R and delay F with respect to the TRAN if 1 switch. So as it is a bidirectional switch, we see here we don't have any we have only turn on and turn off switches, turn off times. In the bidirectional switches, we see only time on and time off switches, turn on and turn off conditions. But here rarely we can see the representations of the time, delay time, rise time, or the turn off time. So here when the control signal changes from 0 to 1, the delay goes with the rise delay. When the control signal changes its transitions from 1 to 0, then the delay goes with the false delay. Okay, and then if you observe the tran if 1 with the delay of 0. So here in the previous slide also we have discussed when the tran if 1, okay, tran if 0. In the previous slide when we have discussed the tran if 0, the same mechanism follows. So the same can be applied to the tran if 1 switch as well. Why? Because the switches are nothing but the bidirectional switches. So here in the bidirectional switches, we don't see, so rarely we can see the turn on rise time and fall time and the turn off time. But mostly in the maximum cases, we will be observing only the two transitions. One is if the transition taking place from 0 to 1, that is from high to low to high, we see the switch will be in the on state. And then the next condition is when the transition is taking place from high to low, that is from 1 to 0, we see the switch will be in the off state. Okay, the time taken for it, the particular switch is to be in the off condition. So this is about the switch primitives with respect to the bidirectional switches and as well as with respect to the resistive switches. The same mechanism will goes with the resistive switches as well. Resistive switches usually we are representing with RNMOS, RPMOS, RCMOS, RTran if 1, RTran if 0, and that's it. So these are nothing but the bidirectional switches. So here we see only two conditions, so, that is on and off state. So today's topic, I think you might have cleared all your doubts regarding the time delays with respect to the switch primitives. Only thing you have to remember in the time delays is the time is confined into three types, that is rise time, fall time, and the turn off time. Rise time is nothing but when the transition takes place, the output when it changes the values from 0 to 1, that is from low to high, then you call that particular time period as a rise time. And then the output when it drives from 1 to 0, then that particular time slot you're calling it as a false time. Okay, and then the turn off time. Turn off time is nothing but it is the values when the output changes with the high impedance value. When it goes with the high impedance value, that is Z or the unknown value X, then such kinds of delays are nothing but the turn off delays. So here the main difference when you consider the switch in the switch primitives, when you observe for the normal switches, we can see the delay representations. The format, the delay representation format, it could we have three types. One is with 1 delay, 2 delay, and 3 delay format. So in the 1 delay format, we usually represent the delay with respect to the one number, whereas in the 2 delay format, we represent with the two numbers, that is with respect to the rise time, and the second one is with respect to the false time. Whereas for the 3 delay format, in the 3rd delay format, we see the delay would be present with respect to 3 delays, 1, 2 and 3. That means what? One is with respect to rise time, the second is with respect to false time, and the third one is with respect to the turn off time. So the main important thing to be remembered in this particular presentation is in the switch primitives, when you compare the switches, the normal switch and the bidirectional switch, when you compare these two, in the normal switch, we can observe the delay would be present in terms of 3 time constraints: rise time, fall time, and delay turn off time. But when it comes to the bidirectional switches, in the bidirectional switches, only the transition takes place either in the 2 state, that is turn on and turn off. So we all know what is turn on and turn off times. Turn on time, T on, is nothing but the time taken for a output to change its the transition from the starting point to the extent after the turn on time is after the rise time is nothing but that particular duration is nothing but the T on time. and later on we see the fall time, right? From the fall time, that means the value which is beyond the turn on time is nothing but the rest of the time delay is nothing but the turn of time. Okay, so here in the bidirectional switches, if you are considering anything, always remember that only we have two kinds of transitions, that is T on and T off states. We don't have any rise time, fall time or delay time. And and also the same mechanism applied with respect to the resistor switches as well. So resistor switches are NMOS, RNMOS, RPMOS, RCMOS, RTRAN, and so on. So the same mechanism follows with respect to the resistor switches as well. And the important thing to remember is this: the block diagram is very important to remember. So this is very important to remember. And in the exam point of view, if you are getting any question based on the time delays pertaining to the 1 delay, 2 delay or 3 delay, and if it is with respect to switch primitives, then the good example is today's representations. You can study well and then give your best. So this is all about the time delays with respect to the switch primitives. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.